So hello people, welcome back to the channel. Today we'll be solving LeetCode daily question 1361, which is validate binary tree nodes. In this, we'll be having n binary tree nodes numbered from 0 to n minus 1, where node I will be having two children, which is left and right, and we have to return true if only if all the given nodes form exactly one valid binary tree. Okay, and it is given that if in the array basically we'll be given three parameters. N will be the total number of nodes, a left child of that particular I and right child of that particular I. So if anytime in the array we find that it is -1, that it means that it is not having the left child, or similarly it will be not be having the right child. Okay, so let's move to the examples. Let's say in this we are having, for the 0th node we are having left child as 1, and okay, let me mark for this we are having left child as 1 and right child as 2. Okay, similarly okay, just a second. Similarly for this for first index I'm not having a left node. Okay, so this is pointing towards null. Okay, so like this is null, and similarly it is not even having the right child, so the right child is also null. Okay, so now for the second node, which is basically this index 3, for second node, yeah, this I'm having left child as 3, as it is here. Left child is 3 and right child is null. Okay, I'm not having any right child, so let me mark. Yeah, I'm not having any right child. Similarly for the third node, I am having left child as -1. Okay, so this is not, and also I'm having a right child as -1. Okay, the right child also does not exist. So this is a valid binary tree. Similarly, if I go for the second example, in which I am having for the 0th node, this node, I am having left child as 1 and right child is 2. Yeah, this is fine. Left child 1 and right child 2. Then for the first, I am having left child as okay, wait, just a second, let me change the color. Yeah, for this, I am having left child as null, okay, which is true. We don't have any left child, and the right child is 3. Okay, right child is 3. This. If I go to the next, then for the second node, I am having left child as 3. Okay, which is not possible because this means that this 3 will be having two parents, and it is not possible in binary tree. Every node must have one parent or no parent, and no parent is only the case when we are having the node or the root node. Okay, like 0 should not have any parent. Okay, so that means this is a binary tree. Okay, so in this is not a binary tree, that's why the output is false, and in this case the output is true. Okay, so this is a simple question of binary trees, and this we can solve using the BFS. Okay, firstly what we need to do, we'll need to find the root node. Okay, so for finding the root node is basically where the uh, it is not having any parent. Okay, root node, to find the root we'll be taking the integer n. We'll be having and the left child array and right child array. I'm just mentioning it left and right. Okay, so this function will tell us which is the root of the given elements. For this we'll be using a set function, a set data structure. Okay, set, and then just simply for I in left childs, I'll be doing let's name set as set. Okay, uh, oh okay, let's name it nodes. Okay, for better understanding, set of nodes, and nodes dot add I. Similarly we'll be moving in the right array. For I in right, what I'll be doing, nodes dot right I. Okay, then I'll be traversing in the for I equal to 0 to I less than n. Okay, so I'll be checking that if not nodes dot contains I. Okay, this means that we'll be simply returning I, that this is the node. Okay, and if this, otherwise this is the case that if let's say there will be loop like for example as seen in the second example, we cannot determine which is the root node. Okay, because it is difficult. Oh no, okay, no. Let's say, let's consider a binary tree. This is still this, we know that this is having root node. Let's consider a binary tree. This is node 0 and this is 1, and similarly let's say we also have a path here from here. Okay, it is also given an example. See this. Okay, we are having left child is 1 and right child -1, and similarly for the one we are having, so this is also a case which is not possible as we cannot determine which is the root node. So in this case we will be simply returning -1. Okay, so let's continue. Yeah, so this function will tell, okay, what this will basically do, that we will be traversing in the set, and if we see that I, which is like the node, for example, if we do the dry run for the first case. Okay, uh, let me copy it, these two arrays. Okay, uh, left child, okay, we are having left child, and this will make firstly in set, set will be look like 1 comma, okay. Oh, and we here also we'll be checking okay, 1 -1 and 3. Okay, uh, 2 also. Okay, as now we can see that we are not having 0 as any child of any, uh, as 0 is not present in a left child or right child. Okay, so this means that our root node is 0. Okay, so this, what this root function will return is the root. So from where we can start our BFS traversal. Okay, just a second. Okay, so now we know what is our root node, and from now here we can move back to the function and we can start our BFS traversal. Okay, so what we'll be doing, firstly we'll be finding what's the name of the function. Let's check. Name of the function is okay, let me just copy it. Validate binary tree nodes. Okay, so firstly we'll be finding the root, so we'll be calling the root function int root will be equal to root of n comma left child comma right child. Okay, uh, just a second, here it will be root equal to root function call. Yeah, and here only that we'll checking that if root is equal to -1, we'll be simply returning false. Okay, so then we'll be having set of nodes which are visited, and we'll be having a queue because we'll be performing a BFS, so we'll be needing a queue for that. Let's name it BFS only, and we'll be simply adding nodes dot add root, and then BFS dot add root. So this is how we'll be starting our BFS. Then we'll be doing while not BFS dot is empty. Okay, firstly let me explain that what is a BFS traversal. BFS is nothing, just okay, let me explain in this tree only. So BFS traversal means that we'll be moving, starting from this node, then we'll be moving to this level, and this, then this. So the BFS traversal for this will be 0 1 2, and then 3. Okay, or the other possible solution could also be you can start by 0, 2, 1, and then 3. It is also known as level order traversal. Okay, so we'll be performing this and we'll be visiting all the nodes in the particular tree. Okay, while BFS is not empty, I'll just be doing let's say current node. Okay, node will be equal to q. Okay, BFS dot remove, and this will be providing us the as I guess everyone knows that how queues work. It is the first in first out. Okay, so we'll be removing the first element from the queue, and then we'll be having a child array. Let's call it child, which will be of the left child of node and right child of node. Okay, so then what we'll be doing, we'll be adding, we'll be traversing in this array for I in child. What we'll be doing, we'll be checking that firstly that if child is not equal, child is equal to -1. Okay, child is equal to -1. Okay, then we'll need to continue. Okay, let's check for this case if child is not equal to -1, and we'll be checking that our nodes, if nodes dot contain I, that this means we have already visited a node and we'll be and it is not possible to have a loop in binary tree, so we'll be simply returning false. Okay, we'll be returning false over here. Then just this if brackets, and if this condition is false, we'll be adding that particular nodes to the I, and then we'll be adding that to that node to the BFS traversal. Okay, BFS dot add I. Okay, and after this, what we'll be doing, we'll be just returning that if return BFS dot size should be equal to, and that this means that we have already we have visited all the nodes. Okay, and this is and the BFS traversal is complete, and it is possible to form a binary tree. Okay, now let's move to the coding window. Firstly, we'll be starting with writing the root function. What we'll be doing, we'll be declaring that function as private. Okay, private int root n comma left array, left child array, similarly right child array. Okay, and then what we'll be doing, we'll be declaring a set of integers, and let's call it nodes. It will be equal to new hash set. Okay, then what we'll be doing, for in node in left array, I will just simply adding nodes dot add node, and then similarly in the other right okay, node in right child, nodes dot add node. Okay, then we'll be using the for loop for I equal to, okay, for basically okay, yeah, I equal to 0, I less than n, and then I will split, and we'll be checking that if not nodes dot contains I will be returning, let's do it this only in the traditional way, return I, otherwise we'll be returning -1. Okay, let's put this into parentheses. Yeah, this looks better. Let's close the parentheses. Similarly, we can do we'll be doing it here also. Okay, so yeah, this is we have written the root function now we'll be finding the root. For that, let's have a variable called root, which will be equal to root function in comma left child and then right child. Okay, and then we'll be checking that if root is equal to -1, we'll be returning false in this case. Okay, then what we'll be doing, we'll be declaring a set of integers. Again, let's call it node set of integers. Set, or let's call it nodes only. Nodes will be equal to new hash set, and then here we'll be declaring queue of integers. Let's call it BFS, which will be equal to new linked list. Okay, so which will be and then we'll be adding nodes dot add root, then BFS dot add root, then we'll be doing while not BFS dot is empty. Okay, we'll be int node will be equal to BFS dot remove. Then we'll be creating a child array, child of size 2 is equal to new and of size 2, and then left child of the node, and then right child of the node. Okay, so then we'll be okay, let's call it children, not child. Okay, and for and child and children, firstly we'll be checking that if nodes dot contains child, this means that we have already visited that node, so we'll be returning here a false, return false. Else okay, also that first that if condition, that if okay, nodes dot contains child and nodes and child should not be equal to -1. Okay, let's add this condition first at the first place. Child is not equal to -1 and nodes dot contains child. Okay, then we'll be returning false. Otherwise, what we'll be doing, we'll be adding this to nodes dot add child. This means that this is already visited, and we'll be then adding this to the BFS. Okay, BFS dot add child. Oh, sorry, not node, child. Okay, so yeah, and after this what we'll be doing, we'll be and if this while loop executes perfectly, then we'll be simply returning return BFS dot size should be equal to n. Okay, this means that we have visited all the nodes. Now let's run it. It should work. Okay, compiler error. Oh, okay, sorry, here it's not possible. Yeah, like this you have to do. BFS next oh, okay, equal to n. Okay, it has given me array index out of one exception at line 14. Okay, what I have to do? Okay, let's create it in the traditional way only. Left child of node and right child of node. That should not be the error. Okay, because yeah, it's giving an index out of one exception, which is okay, and added that BFS also. Okay, let me see through. Okay, so yeah, let me see through it. And okay, I'm just going through nodes. Okay, that this means and when I'm removing the node, it's giving me minus one because that time it is possible. Okay, here. Okay, here it should be if. Okay, I know what's that. If child is not equal to minus one, I have to add it. Okay, then I'll be checking that if nodes dot contains child, then I'll be returning false. Uh, okay, otherwise if the child is not minus one, then I also have to add it to the nodes, the nodes dot add child, and then similarly bfs dot add child. Okay, so now let's run it. Okay, it's giving me a form output. Okay, it's giving me a false. You go to the columns and array finding the root, that's perfect. Nodes and then bfs nodes dot add root, bfs dot add root, and the version for the bfs dot size is not equal to n. Okay, let me try printing the set. Let's see, so this is not equal to print, and then we print the nodes array, nodes, a node set, sorry. Okay, this is 0, 1, 2, 3. Okay, this is size 4. What's that? Oh, okay. So sorry. So sorry. Here it should be nodes dot size. I don't know why I was doing that. My mistake. Yeah, I guess this should work. Yeah, this gets accepted. Yeah. So let's submit it. And yeah, it gets. So this was it for today. Thank you for watching.